Hello, everyone. So today we'll talk about an AMC 10 problem from this year's 2021 Fall AMC 10B. So the problem says distinct lines M and L intersect in the XY plane. They intersect at the origin. The point P at -1, 4 is reflected over L to P prime. And then P prime is reflected about line M to P double prime. The equation of line L is 5x minus y equals 0. The coordinates of P double prime are 4, 1. What is the equation of line M? Okay, so let's take a look at the diagram. So we have this point P, and it gets reflected over to P prime, and then P prime gets reflected over M to P double prime. So yeah, and the two lines intersect at the origin. So one way you could do it is just to coordinate bash, the locations of all the points. One way you could do it is, like this distance from P to this point M would be given by some formula that's like AX0 plus BY0 plus C over that. And you could just coordinate bash all of the lengths and find the coordinates that way, because you can compute this distance, use the Pythagorean theorem to compute that distance once you know this, and so on and so forth. But let's see if we can do a better way to find the to do this problem that involves almost no computation. So to do that, we'll just use this really common reflection theorem. So the setup is this. Let's say you have lines L and M, and they intersect at some point O. So here's L, M, and then let's say we'll just make the acute angle between them like theta. So then if you reflect something about L and then reflect it about M, it's actually a rotation about the intersection point O by 2 theta. So let's just kind of see that it's true for a point, and then it will also be true for figures in general. So I think I'll just draw it for a figure. So let's say you have this sideways smiley face, and then you reflect it over L, right? So it becomes something like that. It's not a very good diagram, but so now it's facing this way, and its mouth is like that. And then you reflect it over M. So let's see if I can draw this. Okay, that's not a very good reflection, but we'll just go with it. So here, the arrow is pointing to the faces, I guess, left. Here, the arrow is pointing to the faces right, and here the arrow of the mouth is pointing to the well, so anyways, it looks something like that. So let's see if we can prove it for a single point. So, if you have this point, P, and you reflect it over to P1 over L, then, one thing you can notice is that, well, by definition of reflection, this is a right angle and those two are equal. So PM equals MP1. And then these two are equal because of side angle sides. So, PMO congruent P1MO as triangles by a side angle side. They share that leg, so their hypotenuses are the same. Okay, so that means P is the same distance from O as P1 is from O. So there's a chance maybe that's a reflection, but that turns out to be not true. And then we reflect P1 over to P2. So here's P2. And then we reflect it. So that's equal to that. That's a right angle. So by the same reasoning, P2 will, that distance to O will be the same distance as P1 is from O. So, it's true that OP equals OP2 in length. So there's a chance that, this is a reflection where, after two there's a chance this is a rotation after, two, which is the same as two reflections. So let's see why this is true. So, a rotation is just, yeah. So let's check the angles, right? We know the distance is okay from the center of rotation. So there's a chance it's a rotation. Let's just test the angles. So if I call this alpha and this alpha, sorry, not that alpha, then this is also alpha. And if I call this beta, then this is also beta. So we can see the line, the angle between the lines. This was theta. So theta was like alpha plus beta. And now we can see that, angle POP2 is just, 2 alpha plus 2 beta. So the angle part of our theorem, could be true. And then the last thing to check to see that it's actually a rotation and not a reflection is to check the orientation of the figure. So, let's just try to draw it a bit better and not use the smiley face analogy. So if I have, let's say a 3, 4, 5 right triangle, 3, 4, 5, I rotated over, I reflected over L. So now it's 3, 4, 5 with the opposite orientation. And now I try to reflect it. Maybe it looks something like that. 3, 4, 5. So you can see, this third figure, let's call it like G double prime. This third triangle, it has the same orientation as the original triangle G, because it goes 3, 4, 5 around in that direction, around the polygon. Here it goes 3, 4, 5 in the same direction around the polygon. In the intermediate figure, it goes 3, 4, 5 in the opposite direction. So this, the orientation is reversed. So if you do a reflection, it flips the orientation. There's no way to rotate G0 to like G prime. But then if you reflect G prime over M, then the orientation is flipped again. So we're back to the original orientation. And you can see that G double prime has the same orientation as G0 because like 3, 4, 5 kind of go around counterclockwise in both figures as the side lengths of the polygon in the counterclockwise order. So yeah, so we've proved 3 things. Orientation is preserved by 2 reflections, so 1 reflection followed by another. The angle is, twice the angle between the 2 lines of reflection. And the distances between the original point and the image after 2 reflections is to the center of rotation is the same, or to the center of the intersection of the lines is the same. So that's enough to conclude that it is in fact a rotation, and the angle of rotation is by twice the, let's say, acute angle between the 2 lines of reflection. So, okay. So we'll just use that to this problem. So, if you draw this diagram again, this is L, this is M. They should pass through the origin, but my drawing skills are bad. So let's just make it a bit better. So you have this point, -1, 4. gets reflected over L to there, and then over M, and then this point P prime gets reflected to P double prime, and it said it was 4, 1 is the location. So let's see here, right? Is this some sort of rotation? Well, by the theorem we just proved it is. It's a rotation about the origin where the two lines intersect. As if you notice, the problem says the lines go through the origin. So then, we have to wonder what is the angle of the rotation, right? So, well, they're both root 17 away, which is kind of irrelevant. But if you notice here, let's say I draw this triangle and this triangle. Then this is 1 and 4. This is 1 and 4. So by SAS congruence, this is alpha and that's alpha. So that means that the angle between the x and y axis is equal to the angle between like the let's just do this in orange, the angle between PO and OP prime or OP double prime. So after two reflections, we kind of rotated by 90 degrees. So then by the theorem, the angle between the two lines of reflection that after composition, made the rotation should be half of 90 degrees. So, by the theorem we just proved, this is 45 degrees because this was 90 degrees. Okay, so then, yeah, we can check that, P double prime is a 90-degree rotation. I guess what is this? Clockwise about O, the origin. So O is the intersection of the two lines of reflection. So yeah, the lines intersect at a 45-degree angle by the previous theorem. So then, we have to wonder, how do I reflect or rotate a line by 45 degrees, right? So normally you would do some sort of rotation matrix, which is like, I don't know, cosine 45, negative sine 45, and apply that to points in the, well, in general, it's by theta, but yeah, this should be 45. So you can apply that to all points in the plane and it'll rotate, about the origin by 45 degrees. But the, since it's 45 degrees, you might wonder, oh, is there a better way to rotate it? And the answer is, well, yeah, there is. So, this line, it was y equals 5x, or the problem said it was like 5x minus y equals 0, which is the same. So let's just kind of, yeah, rotate this. So this line, it passes through 0, 0 and 1, 5. So we can build a square off of this, right? So let's build a square. So this line, it passes through that. But let's just build a square that has one vertex there and an adjacent vertex there. So this square, by the rotation thing, this point is just the 90-degree rotation of this point about the origin. So it will be at 5, negative 1. As you can check with the congruent right triangles thing that we did. So then we just finished building the square. So where is like the other vertex? Well, this is going to be at 6, 4 because we add the coordinates of the vector 1, 5 and the vector 5, negative 1. And well, since this is a 90-degree rotation and this is an angle bisector, then this is 45 and this is 45. You could also, so that means the second line M, it's in fact this line through the diagonal, like this diagonal of the square. So that means this has equation like y equals 2/3 x, because this is 2/3 of that. So yeah, that's the equation of line M. Another way to see it is it passes through the center, which is the midpoint of these two. And that would be have, 3 2, yeah, which is also y equals 2/3 x. So we just get our answer of 3y equals 2x. And that's the equation of line M, which is a 45-degree rotation about the origin of line L. And yeah. So I guess it's D. And that seems like a pretty good place to stop. 2x minus 3y equals 0. Yeah. So yeah, let me know if you have any comments or questions. This theorem about the composition of two reflections is really common. So, you should consider remembering it and understanding why it's by 2 theta and why it's a rotation and not a reflection if you compose two reflections. So yeah, hopefully that was helpful.